Welcome to the Explainer. So let's just dive right in. When you look up and see a drone hovering perfectly still up in the sky, it's honestly incredibly easy to think of it as just a simple remote-controlled toy. But the reality is far more fascinating. What you're actually looking at is a highly complex autonomous organism fighting a constant, high-speed battle against gravity. Today, we're going to break down the anatomy of autonomous flight and explore the invisible systems that keep these incredible machines in the air. Now imagine this scenario for a second. Your drone is hundreds of feet in the air, navigating some complex environment, and suddenly, bam, the GPS signal drops out completely. If a drone relies entirely on GPS to know where it is, how does it avoid instantly plummeting or, crashing straight into a building? Well, this exact rhetorical scenario really highlights the sheer vulnerability of flight. To survive the chaos of the physical world, a drone absolutely cannot just rely on external signals. It requires a deeply sophisticated set of internal senses to maintain its balance and orientation. So here's our roadmap for today's explainer. First, we'll look at the brain of the drone. Second, sensing motion and orientation. Third, navigating the physical world. Fourth, sensor fusion and reliability. And finally, real-world drone applications.
All right, let's start with Section 1, the brain of the drone.
Meet the central nervous system of the entire operation, the flight controller. This is a specialized computer board that essentially acts as the drone's brain. And its primary job isn't actually just steering. It is frantically taking in data from various sensors and making rapid, real-time decisions to adjust the speed of each individual motor. This is exactly what maintains the drone's stability against external forces, like a sudden gust of wind. Now, you might hear about popular boards like Pixhawk, DJI, or Betaflight. Well, each of these caters to different uses, from professional autonomous systems all the way to high-speed racing drones. And they all run highly specific firmware designed to manage these insanely complex flight dynamics. But here's the catch, right? A flight controller is really just a processor. Motors and propellers alone absolutely cannot balance a drone. If a gust of wind hits, the brain needs to know exactly how much the drone tilted in order to correct it. So how does this brain know what it's doing up there in the air without any sensory input? Well, it needs an inner ear. Which brings us perfectly to Section 2, Sensing Motion and Orientation. This is where the Inertial Measurement Unit, or IMU, comes into play. If the flight controller is the brain, the IMU is absolutely the inner ear. It's a critical suite of sensors that continuously feeds the flight controller a non-stop stream of data about the drone's physical orientation and movement. Basically, it's what allows the drone to literally feel its own balance, its rotation, and the constant invisible pull of gravity. Now, the IMU typically consists of two incredibly vital components working together, the gyroscope and the accelerometer. The gyroscope measures angular velocity. Put simply, it tells the drone how fast it's rotating around its pitch, roll, and yaw axes. Meanwhile, the accelerometer measures linear acceleration. It tells the drone its velocity and its orientation relative to the Earth's gravity. Working together, these two provide a complete, real-time picture of the drone's immediate physical motion. But here is the problem. These sensors are incredibly delicate, and that introduces a major vulnerability. Over time, minor inaccuracies in the gyroscope and the accelerometer can accumulate into what's known as drift. That means the drone actually thinks it's perfectly level when it really isn't. They can also get super confused by the vibration noise of the drone's own motors, or even suffer from tiny, built-in manufacturing imperfections known as bias. So while these internal sensors are powerful, they're also quite fragile. Moving on to Section 3, Navigating the Physical World. To actually navigate the outside world, a drone uses a whole variety of tools, but every single one of them has a distinct kryptonite. For instance, the GPS or GNSS provides global location, right? But it can entirely lose signal in urban canyons full of tall buildings or under dense tree foliage. The magnetometer acts as a compass to determine heading, but it's highly sensitive to magnetic interference from the drone's own power wires. Then you've got the barometer, which measures atmospheric pressure to determine altitude, but it can easily be tricked by changing weather or even just the airflow from the drone's own propellers. And optical flow? That uses a camera to track the ground to estimate velocity, but as you might guess, it's completely useless in low light conditions. Because sensors like GPS have these inherent accuracy errors, professional drones rely on augmentation systems. Think of systems like RTK, which stands for Real-Time Kinematic, and SBS as corrective lenses for the drone's GPS. By actively correcting for atmospheric and orbital errors, these augmentation systems allow for incredibly precise, pinpoint outdoor navigation. We're talking centimeter-level accuracy here. Let's look at Section 4, Sensor Fusion and Reliability. So imagine this critical problem. What happens when the barometer senses a drop in air pressure and tells the flight controller the drone is rising, but the GPS data says the exact opposite, that the drone is actually falling? If the brain just takes a wild guess, the drone crashes. So how does the flight controller actually decide what the true reality is? Well, the answer is sensor fusion. This is literally the hero algorithm of autonomous flight. Sensor fusion is the technique of taking all that data from the gyroscopes, the accelerometers, the GPS, and the barometers, and combining it all to create a single, robust, and highly accurate estimate of the drone's true state. It actively filters out the bad information and the noise to give the flight controller one reliable, unified reality to act upon.
One of the absolute most powerful tools for doing this is called the Kalman filter. Let's break down exactly how it outsmarts sensor noise. Step 1, the algorithm uses a mathematical model to actually predict what the drone's next state should be. Step 2, it takes in the new raw measurements from the sensors. In Step 3, it compares that prediction to the actual measurement, effectively filtering out the noise and errors, and then mathematically updates the true state estimate. It is constantly predicting, measuring, and correcting, literally hundreds of times a second.
Yeah, while the Kalman filter is a highly complex predictive model, flight controllers also use what's called a complementary filter. It's a bit simpler, but honestly highly effective. It marries noisy but fast-responding data, like the high-pass data from a gyroscope, with slow but highly accurate data, like the low-pass data from an accelerometer. By fusing the very best traits of both sensors, it creates a super stable and reliable output for the drone to fly on. But algorithms can only do so much if a sensor physically breaks, right? For mission-critical professional drones, avoiding total disaster comes down to redundancy and fault tolerance. This means outfitting the drone with multiple identical backup sensors, like 2 GPS modules or 2 totally separate IMUs. The flight controller is actually programmed to instantly detect a sudden data spike or a complete signal loss. The very moment a failure happens, the system automatically switches to the working backup sensor, or if things are truly critical, it enters a pre-programmed safety mode. However, all of this incredible technology will completely fail without one vital manual step: the pre-flight ritual of sensor calibration. Before a drone even leaves the ground, calibrating the gyroscope on a level surface zeroes out its initial bias. Rotating the drone to calibrate the magnetometer maps out the local magnetic fields. Actually, poor calibration is the single most common cause of novice flight failures. It results in massive drift or completely incorrect headings, which is exactly what you don't want. Which brings us to our final section, Section 5, Real-World Drone Applications. The fusion of these specific sensors empowers some massive real-world impact. Take agriculture, for example. Drones combine GPS and vision sensors for autonomous crop monitoring and hyper-precision pesticide application. In search and rescue operations, drones operate in incredibly complex environments without GPS, using thermal cameras to locate missing persons in extremely low visibility. And in surveying, the fusion of high-resolution cameras, altimeters, and GPS allows teams to build perfectly accurate 3D models of massive construction sites and real estate. It's a total game changer. And you know what? The technology is only accelerating. We're now at the bleeding edge of drone evolution with LiDAR and SLAM. LiDAR uses rapid laser pulses to measure distance and create incredibly detailed maps of the environment. Combine that with computer vision and SLAM, which stands for simultaneous localization and mapping, and you have algorithms that allow a drone to fly into a completely unknown, GPS-denied environment, build a map of that space in real time, and simultaneously localize itself within that brand new map. It's completely independent navigation, and it's absolutely wild to see in action. Which leaves us with this final thought for today's explainer. We've seen how drones have evolved from needing constant human input to utilizing complex sensor fusion just to stay balanced, and now they're literally mapping the unknown in real time. So, what happens when drones can build their own worlds and navigate entirely independent of GPS? The future of self-aware, fully autonomous robotic flight isn't just approaching, it's already here. Thank you so much for joining me for this explainer, and keep your eyes on the skies.